I don't know, maybe Andy, maybe you're on mute, but I'm going to assume that okay, thank you. Anyway, Andy, thank you very much for that introduction, and I thank you for the invitation to give a presentation, the presentation I'm giving today. So yes, this is EarthScope relevant, and it incorporates some EarthScope magnetotelluric data and some magnetic observatory data, such as those collected by the USGS. We're going to use those data to analyze a hazard that is a potential problem for a very important piece of infrastructure that modern society relies upon, and that is the electric power grid. This is a very pretty picture of North America, or of the continental United States, taken at nighttime, and it is a beautiful reminder as to how important electricity is for society. So talking today then about a hazard from space that is manifest at the Earth's surface, and again, which is of concern for the electric power grid industry. I want to say thanks to my collaborators, especially Paul Bedrosian, with whom I have collaborated closely on a lot of this work, and numerous other people who are named here at the bottom of this screen. This work is consistent with the USGS and its mission for pursuing scientific research of societal importance. It's also consistent with a White House project known as SWARM, which stands for Space Weather Operations Response and Mitigation, which is concerned with coordinating work between different federal agencies so that we can address space weather hazards that can interfere with technological systems. Let's see. There we go. So some of this work is actually inspired by what's done in earthquake science. This is a map showing seismic hazard. That is the intensity of shaking that could be realized at different locations in the continental United States or exceeded once per 50 years. So where it's red, we can expect lots of shaking once per 50 years of a certain intensity given by that scale on the right. And I would emphasize that this is a statistical product showing the intensity of shaking for each location. It is not the shaking that you'd expect for a particular earthquake, but it is the shaking that could be realized at each individual location over the span of 50 years. So that's a statistical product displayed as a map, and that serves as some of the inspiration for the work that I will now discuss. So mixed in with this, I'd just like to briefly discuss a few terms which are important and which in different communities have different meanings. What we are not going to be talking about today is risk. Risk is a very interesting word. It is used in the insurance industry to denote the probability that you will lose a particular asset within a certain duration of time. Risk is defined as the product of hazard, such as earthquake hazards, or as I'm going to discuss, geoelectric hazards. So it's a natural phenomenon which can be characterized in some ways in terms of statistics, times the vulnerability of whatever asset you have, and that would depend on engineering or different kinds of technical issues with respect to the asset. And then finally, the exposure of the asset, that is where the asset is located and how it's arranged, for example, on the surface of the Earth. And the product then of those three quantities, hazard, vulnerability, and exposure, gives us risk. So I'm going to be talking about hazard, but this kind of project certainly informs risk. Okay, so before I continue, I just want to give a very brief review of electromagnetism. This is actually undergraduate stuff that I'm just refreshing your mind with. And I'm only doing this is because I understand that some of you may not be living in the world of electromagnetism every day, I just want to bring some of these issues to the forefront of your imagination for the purpose of this talk. So electric fields are defined by electric charges. And if you'd like, you can consider the two equivalent. So when you have electric charges, you have electric fields, and that's known as Coulomb's law. Then we have Ampere's law. And I just want to make sure everybody can see, see that slide. Andy, I'm a little bit worried that this little box is infringing on our viewing here. So I'm just going to move it over to the side there.
Yeah, we don't see that, so you're okay.
Oh, okay, very good. Then the second law I also want to discuss is Ampere's law. Ampere's law basically is a statement that when you have electric currents, you have magnetic fields. So again, electric charges give you electric fields, and electric currents give you magnetic fields. So if you like, you can consider magnetic fields to be equivalent to electric currents. And then the next property is Faraday's law. It's Faraday's law of induction. Time-varying magnetic fields, so time-dependent magnetic fields, can induce or generate electric fields. And then finally, the last law is Ohm's law, which is essentially an empirical relationship, stating that the current that you get in an electrical conductor is proportional to the size of the electric field, and that constant of proportionality is the electrical conductivity of the medium. All right, so all of that's relevant in the context of solar terrestrial interaction, which is nicely summarized in this movie from NASA, showing a coronal mass ejection of electrically conducting plasma flowing out from the sun, and in this case, intersecting with the Earth in its magnetic field. That plasma compresses the magnetic field on the day side, extends it on the night side, and on the night side, as the result of reconnection of magnetic field lines, there is a deposition of electrically charged particles into the upper layers of the atmosphere known as the ionosphere. That causes, among other things, the beautiful aurora borealis that is familiar during a magnetic storm. This solar terrestrial interaction also causes the magnetic field to be active, typically for a day or two. That's known as a magnetic storm. And it is that kind of magnetic activity that, when it interacts with the solid Earth, can generate electric fields in the electrically conducting solid Earth. So what we have then is a very nice interaction between the solid Earth and the surrounding space environment, which is brought about by the fact that the Earth has this magnetic field that essentially connects all the different parts of the Earth. The magnetic field is, of course, generated inside the Earth by a naturally occurring dynamo process, essentially a natural electric generator that generates electric currents and therefore magnetic fields. Those magnetic fields extend up to the surface of the Earth where they can be measured. They extend out into space. That interaction with the sun sometimes brings about magnetic storms, which in turn cause the magnetic field to be active, and that can induce electric fields and currents in the electrically conducting Earth. Now, all of that is conceptually, well, those are simple concepts. This is a very pretty picture of the geology of the Earth. This is the complexity of the real Earth. So this is, for a geologist, of course, a very beautiful representation of the complexity of Earth's history and its structure. That structure, that tectonic structure, that geological structure is spatially complicated, not only laterally in terms of latitude and longitude, but also as a function of depth. And that spatially complicated structure gives us, in the end, a spatially complicated electric conductivity structure. So all of that inductive process that I was discussing in the previous slides and movies is actually made complicated by the structure of the Earth. Okay, so arrayed across the surface of the Earth is, of course, this very important asset, which is the electric power grid infrastructure. Since I'm American and since I'm working for an American agency, I'm showing you United States maps of what the high voltage transmission grid system looks like. And that gives you some understanding about the spatial complexity of the electric power grid. So those two systems, the geology and its geological structure of the Earth and the geography of the electric power grid, are attached to each other because electric power grids are grounded to the surface of the Earth. This is done in order to stabilize the currents that we have in electric power grids. So a typical power grid system is alternating current, and that oscillation in the voltage of the power grid system is designed to be an oscillation about something very close to zero, very close to a zero voltage. What happens during a magnetic storm is that the magnetic activity induces a quasi-steady, quasi-DC geoelectric field in the interior of the Earth. So I say it's quasi-steady because it is slowly varying in comparison to the rather rapid variations that an electric power grid system has, typically at 50 or 60 hertz. So that induction of a geoelectric field in the Earth's electrically conducting interior and it's represented there by this geoelectric field vector, can find its way into the electric power grid system via the grounding connections. So again, we have a technological system which is designed to be operated in a certain way. It's designed to have something close to a zero baseline and to have voltage alternating about that zero baseline. The naturally occurring magnetic activity gives us an electric field that drives a voltage in the power grid system, which is not zero. So that is an uncontrolled DC voltage in that power grid system. And that's really the crux of the problem, the crux of the hazard for the power grid system. Okay, so before I continue, because I expect I have probably a diverse set of listeners in the audience, including solid earth scientists, I just want to briefly discuss some very great magnetic storms. So some of the greatest hits of magnetic storms. The one that is cited as oftentimes as having the most effect on a modern technological system was a magnetic storm that occurred in March 1989. Turns out that's the second largest magnetic storm ever recorded. It induced electric fields and electric currents in the power grid system of the Hydro-Quebec power grid system in Canada and caused its complete collapse, resulting in about $100 million economic damage for Canada. That magnetic storm also caused electric blackouts in Sweden. The largest storm ever recorded, and it's something that some of you may have heard of, occurred in 1859, September 1859. This is known as the Carrington event. It was recorded by old-fashioned analog systems, and in fact, in India, it was recorded by visual measurements of magnetometers. And that turns out is the largest magnetic storm ever recorded. Now, it had it caused a lot of aurora, possibly visible almost everywhere on the night side of the Earth, all the way down to Hawaii, Italy, Cuba, low latitudes, which normally don't see aurora borealis. And it had widespread disruptive effects on the technological system, which was important in those days, which was the telegraph system. So that also being a geographically distributed, electrically conducting system grounded to the Earth. So those are a couple of the greatest hits in terms of magnetic storms. But what's of concern to the United States and other countries is the possibility that we might someday have another magnetic superstorm, possibly as intense as the Carrington event. And there have been, in the United States, a number of studies commissioned to analyze the possible effects that such a storm could have on the American society and its technology. A 2008 National Academy of Sciences study concluded that a replay of a magnetic storm, kind of like the Carrington event, could cause widespread interference with military and civilian communication satellites, widespread disruption of GPS, radio communication, and interference to geophysical surveys, and even widespread loss of electricity, possibly even for months in the United States. And the potential impact for the US economy is actually quite considerable, roughly estimated to be on the order of about $1 trillion. So that's why some of these studies have gained the attention of offices like the White House and its subcommittee called SWARM, which I mentioned in the introduction. So this is actually a picture of a transformer, which was damaged during the 1989 magnetic storm. So transformers, as you probably know, are constructed using windings of electrical wire, and those windings are used to step up or step down the voltage on alternating current systems. As I was indicated in my discussion here, that system is designed to be operated around a zero baseline voltage. And during the magnetic storm of 1989, that zero baseline was disrupted, and that caused a biasing in the operation of this particular transformer and ultimately caused it to heat. So that picture in the upper right-hand corner there shows the coil systems after the magnetic storm, and you can see that they've been burned. So that's actual damage to the transformer, and it is this kind of damage to transformer systems that could possibly result in long-term interruption of electric power systems in the United States should we have another magnetic superstorm. And the reason that would be a long-term interruption is because these transformers are difficult to replace, and it takes time to locate to build them and to position them and to install them and to get them working again. Okay, so that is a break point, and I'm happy to take questions that are about the kind of qualitative discussion which I just presented to you. And if not, otherwise, I'm happy to move on as well.
Yeah, I don't have anything in the queue yet, so so I would say probably just keep pushing ahead, okay, and then we can hit them all at the end.
Okay, thank you, Andy. Okay, so I want to now delve into a little bit more technical detail. Again, the quantity of interest, the hazard, the natural hazard that's of concern to the electric power grid industry is naturally generated electric fields in the electrically conducting earth and their realization at the surface of the earth where the power grids are connected to the earth through ground connections. One thing that sometimes people ask is, well, if that's the natural hazard, then why don't we just monitor the geoelectric field? You can do that. You can install voltmeters into the ground, placing pairs of electrodes and measuring the voltage difference, divide that by the separation distance, and that's an electric field. The challenge is kind of twofold for that. One is that it's difficult to maintain geoelectric monitoring stations for the long term. They're very finicky systems because they get interfered with by all kinds of phenomena, including occasionally lightning, which makes it difficult to operate these systems with the large density that would be required to effectively measure the geoelectric field, say, over the continental United States. The other limiting factor is the spatial complexity of the geological and tectonic structure of the surface of the Earth. And again, that gives us a complicated electrical conductivity, and that results in a spatially complicated geoelectric field. If we were measuring the geoelectric field data, though, this is what some of it would look like. So down here, we have the electric field that's measured at a particular station in Kakioka. They have a project that's dedicated to measuring the geoelectric field for long periods of time, and it's a very useful data set. They have sufficient staff and resources to maintain this, as they have for decades, actually. That is, of course, related to the signal that we have up here, which is the magnetic field variation. So this is magnetic field variation realized over 3 days of time, recording a magnetic storm that occurred in October 2003. That's known as the Halloween storm. So the storm, and if you're accustomed to looking at time series like this, you can see that it started right here with this sudden commencement. That corresponds to the arrival at the Earth of the shock wave in the solar wind, which was related to that coronal mass ejection that occurred at the sun, possibly a couple of days before the commencement of the storm. You'll recall that movie I had in the first part of my presentation. So this is the arrival at the Earth of that coronal mass ejection. And all this activity that's recorded in the horizontal magnetic field components is the storm itself. Now, magnetic induction is, of course, related, as I've said, to the time dependence of magnetic activity. And one way to simply measure that time dependence is to look at first differences in the data. So this is first differences in 1 second data, essentially taking the derivative of this data and plotting it up down here. And then that in turn is related to the induction of the geoelectric field that we see measured down here in the bottom. There's a couple interesting things to recognize here in terms of the geoelectric field. One is that the EY component, that's the east component, is shown in red, and it has a very large amplitude compared to the north-south component, which is shown in black. And that actually is a result of the conductivity structure underneath this station in Kakioka, Japan. As you might imagine, the geology in Japan is three-dimensional, and the conductivity structure underneath the surface of the Earth is three-dimensional, and that structure results in a polarization of the geoelectric field that is measured at Kakioka, Japan. So we have activity in both the north-south and east-west components of the magnetic field. And although there's perhaps a little bit more activity we can see in the north-south magnetic field as opposed to the east-west magnetic field, we see that the result is a very large difference in the geoelectric field. And again, that is due to three-dimensional conductivity structure. The relationship between the measured geomagnetic field and the measured geoelectric field is a set of numbers, which we can call impedance, okay? So it's a tensor that relates the time-dependent relationship between magnetic field activity and the induced geoelectric field. And that can be represented as I'm doing in this very simple chart here. So in the most abstract terms, we have an input signal, and it is being filtered by convolution through an impedance tensor, and we have an output signal. In the case of the Earth, the sun is driving geomagnetic field variation. That is then filtered by the electrical conductivity structure of the Earth to give an output signal, which is the geoelectric field, which is the signal that's of concern for the electric power grid industry. So if you like, that's a forward problem. That's describing the physical cause and effect that is transpiring here. If you're a magnetotelluricist, you measure that cause and effect. You measure the geomagnetic field and the geoelectric field at a particular site. And I would turn this arrow around here. You would use the combination of those two data types to make an inference about the electrical conductivity structure of the solid Earth. So you would use the input signal and the output signal to try to make an inference about the filter that's describing those two measured quantities. So what we are interested in here, in this case, is not making so much an inference of the electrical conductivity structure of the Earth, although that's definitely an interesting problem, but we would like to use essentially the impedance relationship, the measured impedance relationship between the geomagnetic field and the geoelectric field, and to use those quantities, the impedance and the measured geomagnetic field, to estimate the geoelectric field. So we have a set of stations, in this case for North America, shown in those red dots there. Those are the magnetic observatories. including the USGS observatories in the continental United States and also some in Canada. By measuring the magnetic field over the geography of North America, you can fit, if you like, a model to those data. So that is a model of geomagnetic field variation. It's a function of geography. You might mix in a little bit of physics to make sure that it's consistent with the laws of physics. And then we would like to use those maps together with a map of the surface impedance of North America to make an estimate of geoelectric field variation. So this is a model of essentially parameterized induction. And we're doing this instead of making direct measurements of the geoelectric field, because as I was discussing, that's really not practical given the complexity of the Earth and the number of stations you would need to measure the geoelectric field and so on and so forth. What you can do though is use this method of parameterized induction to measure, to estimate the geoelectric field. So that's an ongoing project that we are part of at the USGS, an ongoing collaboration between the USGS, NASA, NOAA, National Science Foundation, EarthScope, and Oregon State University, which is managing the magnetotelluric component of EarthScope. So I briefly want to mention geomagnetic field variation. That's part of this two-component estimation method that we have for estimating geoelectric fields. We have to have an estimate of geomagnetic field variation. This is a pretty picture showing the Fredericksburg Observatory. It's a USGS observatory in Fredericksburg, Virginia. It's been in continuous operation since 1957. It took over for its predecessor observatory, Cheltenham in Maryland, which actually started operating in the year 1901. So these are long-term monitoring stations, which give us an understanding of the history of geomagnetic field variation with the time series that are produced by these magnetic observatories. And I just have to check on my next slide there. With the time series that are collected by these long-running magnetic observatories, we can analyze the statistics of magnetic storms. And if we assume that what's happened in the past gives us some understanding of what might happen in the future, we can extrapolate those statistics to get an understanding of the intensity of a once per 100-year magnetic storm. And we're going to use that together with the impedance to measure or to map geoelectric field variation. Okay, so what we did is we compiled data from a number of very long-running observatories from around the world, and we analyzed their data. So these are stations that have been collecting 1-minute resolution magnetic observatory data for decades, in some cases more than 40 years. So it's a lot of data actually. And we analyzed the statistics of those magnetic field variations. And in this case, I'm showing here at the top a magnetic field record, again, of the Halloween storm of 2003. Remember, I showed you a record from Kakioka, Japan. This is a record from Fredericksburg, Virginia. That pretty picture of that observatory is giving us that pretty observatory is giving us these very pretty data of magnetic field variation. So again, the commencement of the storm is right here, and the subsequent variation over the course of about 2.5 days is the magnetic storm itself. It is a complicated variation, and that complicated variation can be described in terms of Fourier components. So what I'm showing down here are a couple of different Fourier components. I'm showing the amplitude of magnetic field variation at 240 seconds in red and 1200 seconds in black. So those are just example Fourier harmonic amplitudes showing their evolution over the course of time. In this case, for the north-south magnetic component, which is the red component up here, and in this case, for the east-west component, which is the blue component up here. So the point is that we can use those data to identify the amplitudes of magnetic field variations at particular harmonic frequencies. And we then analyze the statistics of those amplitudes, plot them up as a function of amplitude and their occurrence frequency, and in this case on a log-log plot. And we can see that these data don't really quite follow a power law. What they follow actually is a log normal distribution. Okay, so since we have really just a few decades of data to analyze statistically, and since we want to understand the intensity of a magnetic storm such as might be realized once per 100 years, we have to do an extrapolation. We do an extrapolation of those 30 or 40 years of data by fitting a model, a statistical model to the data, and then extrapolating it out to 100 years. That's not actually the biggest extrapolation in the world. It's actually probably pretty safe because we have a pretty good fit model. The model fits the data quite well. And we are going to then look at that extrapolation from multiple stations and understand how it's distributed as a function of latitude, which is what I'm showing down here. So that map where I was showing all those different observatories, we do the statistical analysis of data from all those observatories, and we then do this statistical extrapolation to estimate the intensity of these amplitudes, Fourier amplitudes, for the different stations such as might be realized once per 100 years. So for north-south components, we have the data as shown in red, and for the east-west components, we have the data or the extrapolation shown in blue for those different observatories. And we see that there is a general trend as a function of latitude. So from about 40 degrees latitude up to about 60 degrees latitude, the amplitudes, the extreme event amplitudes for geomagnetic field variation differ by about an order of magnitude. All right, so we have a function then that we fit to those data, and that's what we will use as a statistical estimate of geomagnetic field variation. Again, taking data, doing extrapolation, and making a latitude-dependent map of the kind of geomagnetic field variation we could expect at once every 100 years. So the other component in this whole analysis is the magnetotelluric survey. So that is where the EarthScope part of this whole analysis comes into play. And again, magnetotelluric surveys are supported by EarthScope primarily in order to make inferences about Earth conductivity structure. So here we have a couple of fellows, including Paul Bedrosian, one of my co-authors here on the right, installing a magnetotelluric station. And as Andy mentioned, this project is supported by EarthScope, and that's the location of all the stations that have been or will be surveyed over the course of this project. This project, as you probably know, is managed out of Oregon State University by Adam Schultz, and we are, of course, very grateful that this data are being collected. We're happy to know that it has this new application for analyzing geoelectric hazards as well. Let's see. All right, so one of the things that this magnetotelluric data teaches us is that the geoelectric field that's induced in the Earth during a magnetic storm is spatially very complicated. And again, that relationship between magnetic activity and geoelectric field variation is a quantity known as impedance. So what we're effectively showing here is a map of impedance. Each one of those dots is a magnetotelluric survey site, and the vectors that are the black vectors that are bouncing back and forth show us the polarization and the amplitude of the geoelectric field, such as would be generated by a purely uniform magnetic field variation, which is varying in this case simply sinusoidally. So this is a synthetic calculation. Again, just looking at the geoelectric field variation and geomagnetic field variation for a particular frequency, assuming the magnetic field variation is constant over this piece of geography. It's uniform over that piece of geography. So we're plotting it in this case for 100 seconds and then showing that geoelectric field variation. The first thing you see, of course, is that the vectors of geoelectric field variation are very different in different places. And that's because the impedance is different in different places. In particular, in Minnesota, we see that the impedance is actually quite large. So for a given geomagnetic field variation, the geoelectric field that's generated is actually quite large. And we also see that there is a complicated geographic differences in that geoelectric field. So for example, here in Minnesota, we have these very large vectors, and in a few cases, like right here or right here, the geoelectric field is actually very tiny. So whereas say in other states, like in Michigan or down here in Indiana, the geoelectric field is kind of tiny almost everywhere. All right, so this is a stark demonstration of the importance of the solid Earth for evaluating this space weather hazard. And again, that's what you would get for a uniform geomagnetic field variation, that very non-uniform geoelectric field variation. And that is related, as I think some of you know, to the electrical conductivity structure of the Earth. And this is a map showing the equivalent magnetic resistivity, electrical resistivity in different parts of the northern Midwestern United States. And again, showing very high resistivity here in Minnesota, and also some areas which are quite electrically conducting, juxtaposed right next to that electrically insulating parts of Minnesota. And that is responsible for that geographic complexity in the induced geoelectric field. All right, so I want to distill some of those results down to these maps of scale, these scalar maps of impedance. This shows then, in this case, the geoelectric field that would be generated, the amplitude of geoelectric field that would be generated at different places in the United States for a uniform magnetic field, in this case, a reference magnetic field of 1 nanotesla with a period of 240 seconds. The amplitude of the geoelectric field is shown down here, and that would be measured in millivolts per kilometer. So we see that these red dots, which correspond to the largest amplitude, there's plenty of those in Minnesota. There's some in the eastern United States. Other areas which would be shown, which are represented, for example, by white or yellow dots, show very tiny geoelectric fields being generated. For example, in large parts of the Northwest United States or down here in Florida. So that is essentially a map of impedance because it is showing something proportional to a unit geomagnetic field variation. So that's for 240 seconds. We have it for other periods as well, like at 1200 seconds. When we take then these maps of impedance and marry them to that function that I was describing of extreme event geomagnetic field variation, which we took from the magnetic observatory data, we then get a map of geoelectric hazard. All right, so this is now a statistical map showing the intensity of geoelectric fields that could be realized or exceeded at these different locations on average once per century. All right, and in this case, the amplitude is measured in volts per kilometer. I'll come back to that in a second, volts per kilometer. So the scale is shown down here. Some places, like right up there in Minnesota, have an amplitude that actually is more than 10 volts per kilometer once per century. Other areas, like in these black or gray dots, which we see especially here in the northern Midwestern United States, show amplitudes of between 1 and 10 volts per kilometer. Whereas other areas, like mostly in the Northwest United States and especially down here in Florida, the amplitudes are quite small. So there's big variation, spatial differences in the amplitude of these extreme event geoelectric fields. They're greatest in the northern Midwestern United States. So just to put this in perspective, it was about 2 volts per kilometer that brought down the Quebec system in 1989. So these dots, which are either red, black, or gray, are actually showing quite a substantial hazard. And for the first time, with the Earthscope data and combined with the Magnetic Observatory data, we can understand where these geoelectric hazards are largest in the United States, and actually also where they're smallest. So, and that's the first time we've had that kind of understanding of the spatial granularity of this hazard. So we know now that there are some potentially large geoelectric hazards which could be realized in the northern Midwestern United States. And that's a piece of information that the electric power grid industry can use to design their systems in order to mitigate this hazard. So we would, for example, if we were operating an electric power grid, we would have high voltage power lines which are stretched across large pieces of geography, okay? So across Minnesota, if we were to integrate this geoelectric field, say across a length scale of 100 or maybe 1,000 kilometers, we would integrate this electric field, and that would then give us a voltage of thousands of volts, which would be uncontrolled voltage realized on a power grid system. And this seemingly small voltage, when integrated over the spatial dimension of a power grid, is why there are some substantial voltages that can be realized in a power grid system, which, like I say, are uncontrolled voltages. And that is, again, the nature of the hazard for the power grid. All right, so this shows us the geoelectric field as it would be realized for 240 seconds. We can show it for other amplitudes at 1200 seconds, for example. And again, we believe that this information will be useful for designing electric power grids which are resilient to this surface effect of a space weather hazard. So here are some numbers which come out of those calculations. We find in some cases some very high voltages, sometimes more than 20 volts per kilometer, and those are quite large, but on average or in median, the hazard is actually rather small, but it just happens to be concentrated in certain places. All right, so this is my last slide, and I just want to emphasize a couple of things. One is that I must emphasize that I am a friend of magnetotellurics. I'm not a magnetotelluricist. I've never done a magnetotelluric survey. Maybe that'll happen in the future. But for the time being, I am a friend of magnetotellurics. I like to use their data, and I think that they have a very useful application for evaluating this hazard, this geoelectric hazard, which is of concern for the United States. I think that it would be great if this magnetotelluric survey, a large part of the United States has been surveyed under the Earthscope umbrella, but I would like to see that continued. I think that would be very important for the United States if the magnetotelluric survey of the United States is completed, and even extended into Canada and Mexico, because our electric power systems are actually integrated with those nations. We also need improved geomagnetic field monitoring. So the USGS operates a few observatories. We'd like to have more of those observatories, and of course, we'd like them to continue into the future, their operation to continue into the future. Especially, we'd like to have a few more observatories in the Midwest and in the Northeast. We'd like to extend the geoelectric hazard analysis, such as I've been discussing here, perform magnetic storm scenario analyses. So everything I've discussed today was actually statistical, but you can also look at specific storms and understand the complex magnetic field variation and geoelectric field variation that are associated with specific storms. That's something I would call a scenario analysis. That kind of thing needs to be done. And another thing that needs to be developed, which we're working on here at the USGS, Anna Kelbert and Josh Rigler in particular, are working to develop real-time geoelectric mapping capabilities, and that's being done in collaboration with some of our colleagues at NOAA and at NASA. And then finally, we need to investigate the exposure and vulnerability of the power grid system so that we can estimate the risk that could be realized for an electric power grid system. So with that, that's my last slide, and I'm happy to take any questions.
Great, thanks, Jeffrey. So we have a couple questions queued up, so I'll go through those as others hopefully come in. So the first is from Cecily Wolf, and she asks, are there examples of industry users who are using the geoelectric amplitude impedance exceedance results from your 2016 GRL paper?
Right. Cecily, thank you. That's a great question. I can tell you that there's the electric power grid industry, and by that I mean the North American Electric Reliability Corporation, NERC, is coming to grips with those maps. Those maps are a revelation, actually, and it shows that some of the assumptions that have been made in developing and pursuing projects to improve the resilience of their systems, some of those assumptions they've been making are not very good, not very accurate. And in particular, it shows that some of their systems probably don't need to have anything changed. If you're down in Florida, there's probably not much to worry about. But in the northern Midwest United States, there is. That has not yet percolated up through their understanding and into the kind of the mindset of the regulatory agencies in the United States to motivate any change to the existing regulations that are imposed on power grid systems to make them resilient. It is, however, getting there. So in their latest documents of research that have been proposed by the power grid industry in response to regulator requirements, they discuss our results and they acknowledge that there is a lot more work to do. So that's maybe a long answer to say that they're aware of it, but they haven't quite figured out how to accommodate it. And that therefore actually represents an opportunity for geophysicists, because engineers in the electric power grid industry are not typically, geophysicists. They don't know that much about geophysics. And so geophysicists need to develop tools and products which can be easily used by the engineers in the electric power grid industry. So again, I would say that's an opportunity for future work. There's a lot of opportunity there. And well, I just hope it all gets done.
Okay, next question is from Ross Caton, and he asks, how do the amplitudes of variations in the geomagnetic field during storms compare at high altitude versus the surface of the Earth?
Right. That's interesting. So if you were really at high altitude, like in an airplane, you would see almost no difference between geomagnetic field variations measured in an airplane versus the surface of the Earth, because you're just barely off the surface of the Earth. If you're out in space, you see a lot of difference. So if you're in, say, a satellite that was passing through a current system that's in the magnetosphere, you would see a lot of difference. And you would see a lot of difference because the magnetic field is very active, and you're essentially measuring a different part of the magnetosphere if you're out there. On top of that, you're also moving usually relative to the Earth and to the electric current system in space, and so there is also an aliasing that goes on between your motion relative to the system and the magnetic field variation itself. So.
Okay, and have a question from Paulo Edmundo, and he asks, what is the relevant depth of the apparent resistivity for this research?
Right. So that's a good question. And for the frequencies of interest, which are about 10 seconds out to about 10,000 seconds, it depends on the depth of diffusive penetration depends on the electrical conductivity, but generally speaking, we're talking about depth scales of a few kilometers down to 1,000 kilometers. So it's quite broad. The longer periods are penetrating deeper into the Earth.
So that was the last of the questions that have been submitted. I had one that I wanted to ask, and that'll give, if there's any final questions, time for those to filter in. So the data that you're using for determining the impedances, the MT data, is at 70-kilometer spacing. Is there any indication that there may be structure with shorter wavelength that would be potentially hazardous in between, at sort of a smaller station spacing that isn't caught by this, or is 70 kilometers sufficient to do sort of power grid level research?
Well, one of the things that's great about a survey is you make these measurements and you can get a panoramic perspective as to what all these measurements tell you. And what you can see in looking at those maps of impedance is that there's large areas where there's good coherence in terms of the impedance from one station to maybe 70 kilometers over. So for example, in Michigan or in Indiana, the impedances are not vastly dissimilar. But then when you go to other areas like in northern Minnesota, you see that the impedance from one station to another can be quite different. And so the survey is telling you that there's complicated structure in some of these locations, and that might be an opportunity for a denser survey. So it wouldn't surprise me if someday we want to have a denser survey of northern Minnesota. I'm quite anxious to see the magnetotelluric results for the Northeast United States, which also has very old and complicated geology. And it wouldn't surprise me if we see, we don't know yet, but it would not surprise me if we see some interesting hazards up in that part of the United States. And they might also have a complicated geography, which might in turn mean that someday we might have to have a few more survey stations deployed.
Excellent. Yeah, that's what I was suspecting. Well, great. A couple more questions have filtered in, and so
I'm happy to keep going.
Great, excellent. So one is from Akram Mostafanajad, and Akram asks, did the mid-continent rift have any relation to the large impedance difference in Minnesota that they see?
Yeah, probably, yes. The overall large amplitudes in the geoelectric field that you see in Minnesota is due to the fact that that is old cratonic geology, very resistive in general. There are some spots, however, which also have good electrical conductivity, and some of that might have been brought about by the mid-continental rift, yes.
Okay, then there's a question from Patrick Taylor that asks, since earthquakes move conducting material through the Earth's magnetic field, is there any kind of observable signal from seismicity?
Okay, well, that's an interesting question. It's just so we all know that's not related to what I was just talking about, but that's okay. So what the question is, if we have an electrical conductor that's like parts of the Earth that are moving relative to the ambient geomagnetic field, does that induce anything? And I don't know that there's a measurable signal in that sense related to the motion of the solid Earth during an earthquake. But what there is the generation of waves in the ionosphere that respond to the earthquake, and the motion of the ionosphere relative to the ambient geomagnetic field does generate a magnetic perturbation that can be measured at the surface of the Earth. So that's one thing. Another way that this kind of induction can be realized is during a tsunami. So when the motion of the ocean, which is a good electrical conductor relative to the ambient magnetic field, generates a perturbation in the magnetic field, which some say can be measured. I haven't investigated that myself, but I've read papers on it. I might be forgetting something, but that's the answer to that question that I provide for now.
All right, thanks, Jeffrey. Well, that is the last of the questions that I have received. So I would, if anybody has any follow-ups, I don't know if you're available over email, Jeff, if somebody has a question that
Yeah.
comes up later on.
I'm happy to field questions, and it actually is part of my job. I get all kinds of questions from different people of different persuasions, and so if you have questions, I'm happy to field them. I also have papers on my staff profile at the USGS, which you can check out.
Great. Well, I will. I think we'll end the webinar there. Jeffrey, thanks so much. That was great, and this will be up on YouTube shortly. So if anybody knows somebody who missed out and they were interested, they can find it there. But have a good weekend, or have a good afternoon, everybody, and a good rest of the week. And thanks again, Jeffrey.
Thank you.